The next topic we're going to discuss is how parallel programs can be developed using modern Java features. And this is actually a really fun topic, and it'll start segueing into what we'll be covering here in the course. So, turns out that Java is a hybrid language that has support for object-oriented programming and also for functional programming. And so we're going to focus primarily on its functional programming parallel processing frameworks, although I'll talk briefly about an object-oriented framework as well. So the first framework we're going to talk about here, and I'm just going to give you the quick overview here and then dive into it deeper when we get into the bulk of the slides, are fork join pools, and that's an object-oriented parallelism framework. And you'll see, we'll talk about how that works in just a bit. The next model, which we'll spend a lot more time on in this course, is parallel streams, which is a synchronous functional programming framework. Synchronous meaning that you typically use it with blocking calls, and because of the way that threads are allocated, you can afford to block, which is good. And then we'll talk about something called completable futures. And completable futures are so-called reactive or asynchronous parallel functional programming. And the idea basically there is you are going to start operations running in the background, and then as they complete, you're going to get the results and do some further processing, putting other work in the background. So it's a very cool model, and we'll get a chance to talk about that. And then we'll also spend time in this class talking about reactive streams. And that's, in my mind, the most exciting thing we'll be covering. Not that the other stuff isn't exciting too, but this is going to be a big focus, and it's a very modern approach. And it basically is an asynchronous programming paradigm that's concerned with processing streams of data and propagating changes. And what you'll see when we get to this discussion later is that reactive streams kind of take some of the characteristics of Java sequential and parallel streams and kind of take some of the characteristics of Java completable futures in order to be able to provide a more holistic asynchronous parallel programming model. So really, really cool stuff. So let's talk about some of these things in a little bit of depth. So Java 7, which came out about a decade ago, introduced an object-oriented framework called the fork join framework, or the fork join pool framework. And you can learn more about this framework here at this link. It's an interview with my good friend and colleague Doug Lee, who developed the fork join framework. And it provides high-performance, fine-grained task execution for data parallelism. So let's kind of break that down a little bit. So high performance means that we want it to run fast. Fine-grained task execution means that you can have thousands or tens of thousands or hundreds of thousands or millions of tasks that are running. So each task can be very small, and you can have a lot of them, so it's small granularity. And data parallelism means that we use data as the means to make things run in parallel. What that essentially means is we're going to take a big source of data, and we're going to break it up into chunks. Gee, this should sound familiar, right? This is divide and conquer we just talked about. And we're going to use something called fork. We're going to fork things until we get very small chunks of data with maybe one element or just a couple of elements in them. And then we're going to process those elements of data sequentially, but we're going to do them all in parallel. So again, each individual thing is done sequentially, but the aggregate or the combination is all done in parallel. And then as everything finishes, we're going to join it all back together again until we get a final reduced result. So that's what high-performance, fine-grained task execution for data parallelism is. There's other earlier models in Java, like the Java Executor Framework, which supported a more coarse-grained, task-oriented model of parallelism. And we're not going to focus on that. That will be the focus of the class I teach in the spring. So the way that the fork join framework behaves is to solve parallel programming problems by divide and conquer. So you can read more about divide and conquer here. I hope by this point you've been introduced to divide and conquer, because it's the kind of thing you would have learned about in stuff like your courses on algorithms. Divide and conquer is typically used for sorting algorithms, things like heap sort or merge sort or quick sort. Those are examples of divide and conquer. And the way that works is if the problem you have to work with is small, then you just solve the problem sequentially. Otherwise, you split the problem up into independent parts, hopefully evenly and efficiently. You fork new subtasks to solve each part. You then join all the subtasks and you compose the results together from the subresults to create a final reduced result. So that's divide and conquer. And again, think about merge sort or heap sort or quick sort, same kind of idea. The way that the fork join pool works is by this process called work stealing, which is intentionally designed to maximize or optimize the performance on multi-core processors. And in a nutshell, the idea is you want to keep the cores as busy as possible. Cores aren't like us. They don't need a break. You know, if you give them work, they're happy. They want more work. And so what they do is they take the work and they split it up into these subtasks, and each thread that's in the fork join pool has a little queue. It's actually a double-ended queue called a deck. Has a queue of tasks waiting for it to do. So, you know, what is a queue? A queue is a data structure. It's a first in, first out discipline protocol. So whatever's been there the longest is the next thing to get pulled out. And so there's a deck, double-ended queue, so you can insert things at either end and remove things from either end. And each thread will work on items in its deck. But if it gets to a point where it doesn't have any items in its deck, rather than spin or block, it'll go and look at somebody else's deck, some other thread's deck, and will try to steal work from the tail of the other deck. And there's various reasons why it steals from the tail that we'll talk about when we get to this in more detail. But it tries to steal work, and if it can steal work, then it keeps going. So the idea is you want all the cores to be cranking away doing something productive, and if they run out of work on their own, they go take somebody else's work and work on it, because they're considerate and nice. And that helps to maximize processor utilization. Your cores are firing on all full cylinders. Java 8, which transitions into what we now call modern Java, added 2 new parallel functional programming frameworks. And the first one is parallel streams. We're going to pivot, as soon as we get done with this intro, into streams and parallel streams. And you can actually go to my website if you want to sort of read ahead. If you go back and watch last year's YouTube playlist for this class, if you go and look at my YouTube channel, you'll see that there's playlist. Actually, if you go to my website, which I think I pointed out before, I have all my classes listed for the past decade or so with all the videos there. And if you go for the ones from fall of 2020, you'll see all the material there. This class will cover different stuff, but there's a whole bunch of stuff there on Java sequential streams. So you might want to watch those videos if you want to kind of get a head start, because we're going to start that probably either at the end of the class or on Wednesday. But this will give you a chance to start early if you want to. So parallel streams are a variant of streams. We'll talk more about streams. And it's used to partition streams, which are basically just chains of processing operations that work on data as it traverses through the pipeline of these connected operations. It partitions a stream into multiple substreams that run independently of each other on different threads and can be combined into a reduced result. So you can think of parallel streams as basically a functional programming facade atop of the Java fork join framework, which is an object-oriented framework. And what's cool about parallel streams, and you'll see this when you get to play with this in assignment 1B, which will come out later this month, or later in September, because we're almost at the end of this month. Basically, parallel streams takes chunks of data and it maps them to multiple threads, which are themselves mapped to multiple cores. And all this stuff takes place under the hood. You don't actually see what happens. You just take a stream and you say, make it a parallel stream, and boom, all of a sudden everything's running in parallel, which is really, really cool. As I mentioned before, under the hood, it leverages the common fork join pool. So the common fork join pool is this Java 7 object-oriented framework, which has got this kind of new lease on life by being the engine for doing the computations for parallel computing with parallel streams. I'll also mention, we had talked last week about the new feature that'll come out in Java 18 or whenever called virtual threads. And the fork join pool at the moment is also used as the scheduler for virtual threads. So you can have millions of virtual threads or millions of tasks that are running in the common fork join pool, and it handles it very scalably and it helps with throughput and latency and so on. So the way to think about parallel streams is basically high performance, fine-grained data parallelism with a functional programming veneer, a functional programming facade. So functional programming has been wrapped around the edges of the object-oriented fork join pool framework and gives you this nicer way of programming. The second model that we're going to talk about, you'll get a chance to play around with, are called completable futures. And completable futures are basically a way of being able to support dependent actions that are triggered upon the completion of async operations. What the heck does that mean? Well, let's take a look at a simple example. So this is a fun example we'll talk about, and I'll walk through in a couple different ways. That is going to be a web crawler. You're implementing a web crawler for your programming assignments. This is a variant of that. And so in this particular case, we have task 1, which will asynchronously download a given web page. And it gets back something called a completable future, which I represent here as a table tent number. If you ever go to a banquet, or if you go to a fast food restaurant where you order food and they give you a little plastic number, sometimes you put them like in a little holder, sometimes you put them on your table. Those are called table tent numbers. So they represent a pending obligation to deliver you something. So we say, I would like to asynchronously get the start page for HTML, and then we fork off 2 other tasks that will run asynchronously when task 1 completes. So when task 1 completes, then task 2 will count the number of images on the current page. Task 3 will, in parallel, go and crawl all the hyperlinks that are reachable from that page after it completes again. And then task 4 is going to wait till task 2 and task 3 are done, and it will combine the results together and come up with a sum of the results. Yeah? Great questions. The question is a completable future similar to a promise in JavaScript? Yes, very much the same. Very, very much the same. Same basic idea. And this, again, takes advantage of the underlying hardware. It takes advantage of the multi-core processors. It takes advantage of the underlying fork join pool. And so it does a lot of the other things. It just is a very asynchronous way of doing things. So essentially what happens here is all the stuff I've kind of highlighted in red here, like then apply async, then compose async, supply async, and so on. These are part of the asynchronous computation model in completable futures, where the caller, the thread that invokes the operation, doesn't block waiting for the callee to complete. The caller will go off and do other things. The callee will do other things too. So things are running in the background, and then when these dependent actions finish, then they will trigger other dependent actions. So when the computation's finished, when the asynchronous operations finish, dependent actions are triggered as a result. These asynchronous operations can run in parallel and thread pools. And unlike the Java parallel streams framework, which uses the common fork join pool, there's a common fork join pool, we'll talk about that later. The nice thing about completable futures is you can define what thread pool you want it to run in. So it gives you a little bit more flexibility. So you could use lots of different types of thread pools. You could use a cache thread pool, you could use a fixed size thread pool, you could use the fork join pool, you can have your own custom thread pools if you so desire. It's possible to combine Java completable futures and Java streams, typically sequential streams, not parallel streams, together to have a good outcome. Kind of like taking peanut butter and chocolate and making a peanut butter cup, which is like one of my favorite foods. I've actually run into people who don't like peanut butter cups. I just can't understand them to save my life. Java 9 then added something called the Flow API. So this is, again, a modern Java thing. And as you can see here, the Flow API is just a set of interfaces. There's a publisher, a subscriber, a subscription, and a processor. And as you can see from looking at the methods that are disclosed here in this interface, there's not a whole lot of stuff going on in some ways. Not a lot of methods, at least. And the reactive streams model in Java 9 implements a stream-oriented pub-sub framework using 2 patterns that you're probably familiar with. And the first pattern is the iterator pattern. And the way that works is a subscriber can pull items from a publisher. The subscriber can basically say, send me 10 items to process, please. So you can see the subscriber says, these are the number of items I can handle at this point. And then the publisher says, okay, boss, here you go. I'll send you that many items. And then the subscriber will go ahead and process them. So that's one pattern it supports. And then the other pattern it supports is the observer pattern, which is a push model where the publisher pushes the data to the subscribers, because there could be multiple subscribers. Remember, the observer pattern could have multiple subscribers. It could also be multiple subscribers here. And the source pushes the data to the sink. So streams are basically observer plus iterator. Both of those are good old gang of four patterns that hopefully you've seen before. We're going to be talking about one implementation of reactive streams. There's a bunch of them. There's RxJava, which is one of the early ones. There's something called Project Reactor. There's other implementations in other languages. There's variants of this in JavaScript. There's variants of this in languages like Scala and so on. But we're going to focus on something called Project Reactor, and you get a chance to play around with this stuff. All of these Java frameworks often eliminate any need whatsoever in your program, the program that you write, for synchronization, for locks, as well as eliminate the need for explicit threading. You rarely, if ever, have to create a thread. You rarely, if ever, have to destroy a thread. So all the threading and all the synchronization is handled underneath the hood by the frameworks. And this is nice because it eliminates many accidental and inherent complexities of parallel programming. So the less you have to worry about, the less things can go wrong. Not to say that other things can't go wrong, but you won't have problems with some of those basic building block parts. So, as I mentioned before, the Java parallel streams and completable future functional frameworks use the object-oriented fork join framework by default, although there are some ways to overcome that. The various reactive streams implementations can use the fork join framework, but they often come with their own internal pools that are designed in a slightly different way for other purposes. Okay, so that's an overview of how parallel programs are developed in Java. We're going to spend the bulk of the semester focusing on those programming models.